Well, in this segment, we will go over an alternative way of calculating a magnetic field that's useful in cases of high symmetry, and that's the method known as using Ampere's law. So let's talk a little bit about where this law and where it came from. Uh, the Biot-Savart law, as we've seen, is in general difficult to use. Magnetic forces in general are tough things to visualize and to find the directions of the forces, etc. And magnetic field directions. The Biot-Savart law here is almost as complicated as it could get. First of all, it only applies for an infinitesimal length of wire with a current I through it, so there's my infinitesimal. If I want to find the magnetic field that it produces at a particular point, then I draw the vector R vector that points from the current infinitesimal current element IDL vector to the point where I want the field, and those will determine a plane unless they're collinear. Okay? And so I'm assuming that they're not collinear, and so I can get the plane of R vector and the DL vector. This angle in that plane between DL vector and R is just the cosine, is just the angle theta that we typically talk about between the two. B vector, dB vector, in this expression is perpendicular to that plane via the right-hand rule. And as I say, it's not easy because you've got a right-hand rule because of this vector product of things, and then also this is just part of the current, and any current comes out of a current loop, and so ultimately you have to integrate around an entire circuit to get a total magnetic field, even at a single point. So people began to look for better ways, and one of the ways I think we did last time, we talked a little bit about the Gauss's law of magnetism, which is sort of analogous to the Gauss's law for electrostatics, or just called Gauss's law usually. And we found that it's just not much going to be of much use, or it wasn't found to be of much use in finding B, the Gauss's law of magnetism. In electrostatics, Gauss's law is of use in highly symmetric charge distribution cases, and we did the examples of that when we were looking at Gauss's law. But Ampere found a way to find B for a known current that is similar. It's not exactly the same, but it's similar to the way Gauss's law in electrostatics is used. And the way he did was, in developing it, was to look at this, go back to the original long, infinite straight wire carrying I, and get a distance R away from it, and we know that the magnetic field swirls about it in this sense. And we'd written this expression for it. That was really due to Ørsted. He had essentially discovered that result. And Ampere was familiar with fluid mechanics, and there's a similar kind of situation where a physical quantity swirls and sort of these circular swirls about it, and that's in the studying of eddies in fluids. Okay? Eddy is like a vortex, a whirlpool, and people had found it useful to define an expression like this, where instead of B, magnetic field, they had V, the fluid flow velocity. And for whirlpools and eddies, the larger this integral was as you integrated all the way around the whirlpool, was larger. So a very strong eddy had a large circulation. In fact, that's what they call this, the circulation of a fluid. And by analogy, Ampere realizes that this is kind of like that, and so it might be useful to calculate something analogous to that circulation And so he began to look at calculating for this particular situation, the integral around a closed curve, b dot dl. Curves are one-dimensional things. They're just lines, and the fact that I've got, so that's the one integral sign, and then the circle in it to indicate that this is a closed curve. So it's sort of mathematical notation that's in standard use. I'm going to get on the top and look down on this from above, and so if I do look down on top of that, then what I see is pictures like this. I've got I coming out at me. I can define a circular curve in that plane that's up here, in this plane perpendicular to the wire. It could be any plane, but it has to be perpendicular. I go out a distance r on it, and I know what the magnetic field is at that point. It's just given by this expression here, at least the magnitude of it, and it's in that direction in this fashion. This is the field. I'm at a distance r, and then I have defined a curve C that's a circle with the center at the center of the wire, and then dl vector is a little infinitesimal segment of that in the same direction in this case. And you can compute, one way to compute it is just take b dot dl, which is the magnitude of b times the magnitude of dl times the cosine of the angle between the two. But you can see that this dl is always tangential to the curve, and that's always perpendicular to the radius, and b is in the same direction, so the angle between them is 0. Magnitude of b is just this mu naught I over 2 pi r. R is the distance from the center, and then dl and cosine is just 1. So you can certainly get it that way. Or another way that you could do it is to substitute in that vector expression. Remember, the theta hat direction is if I grab the wire with my thumb pointing in the direction of current flow, that my fingers naturally curl in the direction at a given point up here in the direction of theta hat. And so both b and dl vector, as dl and the theta hat, are both in the same direction, and so theta hat dot theta hat is just 1. So either way you feel comfortable with, you can compute these b dot dl's. And so I'm down to this. And now then, in this case, I'm going around this curve, but it's always, what defines the circular curve is the fact that it has constant r. And so long as the current I is a steady current, which is what we're looking at here, then mu naught I, 2 pi, and r are all constant on this on that circle, on the curve. And so I can bring all of those outside, and then I just have to add up all the dl's all the way around this curve. Well, it's magnitude dl, and if I add up all the magnitudes, that's just the total length around that curve, which is just the circumference of a circle of radius r. So this whole length around is 2 pi r, which cancels the 2 pi r on the bottom, and we get that around that circle it was mu naught I. This is the current. The current direction of current is right through this dead center of the circle. Well, what if the curve that you choose is not a circle, but still closes on itself and still goes around the wire? And I'm going to look at it now in a different direction just to get a different perspective. I'm going to come up here and now I'll be looking from the bottom up. And if I look from the bottom up perpendicular to this plane, the current flow is away from me. And that's what I've got here. Looking from the bottom up, the current I is going away from me. And now then I'm going to choose a new curve that's not a circle, but is going around it in this sense. I could have chosen the other direction, and it would be the same argument. But here I'm choosing remember, curves you have to give the direction in which you're going to integrate around, and so that's usually indicated by the arrows. It's still a long wire, and if you look at this with the magnetic field is go out a radius to say this point here, then B is going to be at right angles to it by the Ørsted's law, and dl vector, and I've got it going at some slant. If I draw a line to the center here, then this dl subtends an angle d phi total. And again, I can do the same thing. I'm going to calculate the sum over all the b dot dl's. But let's just look at the b dot dl here. B dot dl is the magnitude of b, the magnitude of dl, times the cosine of the angle theta. And the angle is theta is between b and dl vector. And there I've got it drawn in this plane as this angle between those two. So here the angle isn't 0 degrees, but is something other than 0 degrees. But I do know that this is a right angle. So this direction over here is basically a right angle. It's a radius, essentially. And so there's a right angle here. And the cosine of theta is just going to be this arc length along a circle of radius r, there's a great circle here, and along that direction. So that would be the arc length, and I can get that the cosine of theta, with this right angle being here, is the adjacent side over the hypotenuse of this little right triangle, and that's the adjacent side is ds, the arc length, and dl is the length of along the curve up here. Well, the arc length, that's this length here. If I know an angle theta, the arc length in a circle is just s. The arc length is just the radius times the angle theta if I measure theta in radians. And if I do it infinitesimally, then ds is equal to r d theta. And that's what I'll use up here. Ds is r, well, in our case, since I've already got the angle theta, I call this d phi. So this arc length, this side, is simply r ds, which is r times d phi. It's a big circle here, and you've got this arc length along the circle. So I get this, and then I can rearrange that to get just multiply through by dl. dl cosine theta is the same thing as r d phi, at least as far as we go to infinitesimals. Well, I've got dl cosine theta over here. So this b dot dl vector is b dl cosine theta, but dl cosine theta is r d phi, so I can substitute for the dl cosine theta r d phi. And so we're down to this. This integral b dot dl is the same as the integral all the way around this curve of b times r d phi. But I know what the magnetic field is at this point. That's just the result of Ørsted for a long infinite wire. It's mu naught I 2 pi r, where r is the distance from it. This distance to this point here from the wire. And again, the r's go out, which is nice, right? Because now it doesn't really matter which piece I'm looking at, because as I go around different dl's, I'm going to get different r's, but they'll just be canceled out. At each point, I'll have a r at this side. This may be larger or shorter, this one, but the r's will always cancel. And then mu naught I, I've got a steady current, 2 pi, pull that outside. And now it's just an integral all the way around that curve of the angle of d phi. So if I start at some point, maybe straight up, as 0 phi, and go all the way around this curve, the angle will go all the way around from 0 to 360 degrees, or 2 pi radians. Remember, we had to have angles in to make this computation. We have to have the angle d phi in radians. So to go all the way around it, d phi simply is the total angle in 360 degrees, and that's 2 pi radians, and the 2 pi's go out. And again, we get the same expression as for the circle, but now we've generalized it. C can now be not just circles with the wire at the center, but can be any closed curve that wraps around the eye, around the current. So this shape could be anything. It just has to close on itself, and it has to enclose or wrap around the current carrying wire. Well, finally, what if the closed curve that we chose lies totally outside the current carrying wire? So now I've got a different C that I'm going to go around in this fashion. But it lies totally outside. It doesn't wrap around the wire at all. And it's really the same calculation as before. It's just the same exercise. We're looking at B dot dl, which is B dl cosine theta, but dl cosine theta is the same as r d phi. So this integral around the B dl's is the integral of B dl cosine theta. dl cosine theta is r d phi, so I get r d phi here. And now it's the integral around this closed curve up there. But the magnetic field produced by the wire is still that of Ørsted, mu naught I over 2 pi r. The r's still cancel, and I'm down to this expression all the way around the closed wire. What's different now, though, if you look at it, let's say I start over here, and I go around this closed wire. So my angle phi is going to increase as I come over here to whatever its maximum is at some point. So phi would go from whatever this angle is to phi over to this angle. And now then, as I come back along the bottom edge here, now my angle is going to decrease, and finally it comes back and I'm back to whatever the angle was at I. So this integral now, when it's outside, I get the integral from I coming out, coming back, from I to I, wherever I started along that curve, and that just gives me the angle phi at I minus the angle phi at I where I started, and so phi of I minus phi of I is 0. And so if it's outside, the circulation is 0, the integral of B dot dl, if C does not wrap around the wire. Well, that in essence is one form of Ampere's law, that this integral of B dot dl around any closed curve C is one of two results. It's either 0 if the closed curve doesn't wrap around the current, or it's equal to mu naught I if C does wrap around it. It can be any shape. It just has to be a closed curve. Well, to utilize it, there's several conventions that are used, and one way is I'll have a current carrying wire coming out of the page at me. And I'll think about a curve C1 in which I go clockwise around it here. And what one does, a closed curve always encloses an area, and that area has a perpendicular to it. And the way you get the perpendicular, or the normal, to that area enclosed by the curve C1 is you pretend like you grab the curve C1, any one of these points, with your thumb pointing in the direction of the way you're walking around the curve, going around the curve, and then your fingers will naturally curve through the area enclosed by the curve and the direction of, by convention, is the positive normal to it. So this closed curve has a normal in the end of the page. If I go around it counterclockwise here, again, you can grab it. Your fingers will naturally go around the curve, and the arrow, your fingers will naturally curve around through the area enclosed, coming up out of the page. And so if I go around it this direction, it's one normal is chosen by convention. If I go around this way, I get the outward normal. And then the using that convention, essentially we use the normal to define the direction of positive current flow. So if the current is flowing through the area enclosed by the curve in the opposite direction to its normal, then we would call that a negative current. If it's going in the same direction as the normal to the area enclosed, that's would be called a positive current. So this integral is a 0 if you don't enclose any I, and if you have this orientation going around it this direction, you would call that a minus I, so you get this. But if you were going around it in this clockwise fashion, same curve in both cases, you'd get a plus mu naught I, and that's really just the sign conventions that are used. But it changes the focus now to the area enclosed by the curve. Let's give a quick example here. Let's suppose I've got several currents, I1, I2 going into the page, I1 coming up, I3 coming up, and I4 going into the page. So all long wires. Right? And then I choose a curve that's here, going around it in this fashion. So I choose a specific curve and the direction that I'm going to integrate around it. Then the integral of b dot dl, well, anything that lies outside the area enclosed by that curve doesn't count. So there is no I4 over here. I choose my normal to it using that right-hand rule, thumb pointing in the direction of the arrows going around the curve, and then your fingers naturally curve through the area enclosed in the direction of n hat, so that's this direction. And if a current I is going in the same direction as n hat through the surface, then it's positive. If it's going in the opposite direction, it's negative. And so we would get a contribution, since all of these, I1, I2, and I3 are all enclosed, are inside, cutting the area enclosed by the curve. I, since it's coming the same direction as n hat, is plus I1. I3 is plus I3. But I2 is going in the opposite direction, and so it's a minus sign, opposite to the normal of the area enclosed. Well, that's really the best way to state Ampere's law, and that is that this integral of b dot dl is equal to mu naught times the total current cutting the area enclosed by C, again honoring that that sign convention for the normal of the area enclosed. Remember, areas are area vectors, and so you have to have a normal. Well, that is Ampere's law in all of its glory. And Ampere's law is another one of these laws that is it holds in general for steady currents. So we've always been assuming that we have a constant DC current, so all currents are constant. And then to be really useful, there has to be a high degree of symmetry in the problem, so that you can use the symmetry to compute the magnetic field. That was a condition that we found with Gauss's law as well. So this law here, we'll see how to apply it in a method analogous to, but not exactly the same as Gauss's law. So, and again, the the only things that have to apply for it to be used is it only holds, Ampere's law only holds for constant current, so you can't have any time varying currents. And then we have to have a highly symmetric case.